Hey guys, I'm Srinivas Varadharajan. I'm a machine learning engineer part of HPC and AI Innovation Lab at Austin, Texas. In this video, we'll be looking at an overview of various tasks performed part of object detection in overhead imagery, followed by a short demo to detect objects in satellite images. Here, we will be using XView satellite imagery dataset as an example. To start, how does deep learning algorithms learn to predict what they predict? What are some of the common tasks in any machine learning project? Where to start once the purpose and objective of the use case is defined? So the first steps after identifying the objective is to collect raw data, which is required, and this would help the machine learning models to learn the patterns. Depending on the use case and the objective, we can start by deciding if we need to acquire new data or curate existing data for our purpose. XView pulls satellite images from wide variety of geographical location, with each location having its own distinct features, which includes physical differences such as plains, deserts, coastal regions, differences in construction such as varied layout of houses, cities, roads, etc. Now the data is collected, but how would the algorithm know what is present in an image? This is where data labeling comes into picture. In a supervised learning approach, we use data labels to let the algorithm know what is present in an image. It is basically a process of adding context and meaningful information in form of labels to the collected data. In the XView dataset, axis aligned bounding boxes that tightly contained object instances were drawn, and labels such as cars, trucks, buildings, etc. were assigned to the object instances. Next is the interesting part, training a machine learning model. Training in machine learning generally refers to a process in which algorithms iteratively learn the patterns in data, predict and fine-tune the parameters, thereby improving the accuracy. Finally, the inference. Using the trained model to predict the required information from an unseen data. This is the one of the main objective of inference. During the model training step, we showed the algorithm what the data contains in form of labels. But during the inference, the model must make the predictions based on unseen observations. The accuracy here is also very dependent on how the machine learning model was generalized during the training step. XView is one of the largest and most diverse publicly available overhead imagery for object detection. It contains over 1 million annotated bounding boxes, which is over a million object instances in over 1,400 square kilometers of imagery. Each object instance represents one of the 60 classes defined, which we'll be looking in detail in the upcoming slides. The dataset could be used in various research directions, such as domain adaptation, as the dataset has a great geographical diversity. The objective in our demo is to identify the objects and predict the bounding box for each object in the image. The dataset consists of around 1,400 images, which is divided into training, validation, and test sets. Roughly 60% of the data is used for training, 20% for validation and test sets. Over 600,000 objects are present in training and 200,000 objects are present in validation sets. The 60 object categories such as buildings, bus, container ship, cargo plane, etc. are organized into 7 parent classes such as fixed wing aircraft, passenger vehicle, building, truck, railway vehicle, maritime vessel, and engineering vessel. Most of the objects in the data set belong to these 7 parent classes. The left side image shows input data, and the right side image shows bounding boxes rendered on top of input data. This illustrates how dense the objects are present in the data set and the amount of objects in a single image. So once the data is collected and data is labeled, we go to this next step, which is nothing but training. So to start training, we normally start with, most of the time it's by using one of the baseline models. So the baseline model that was used here for training is SSD, single shot multi-box detector. It is one of the popular models used for object detection. It basically performs both object classification and localization in a single forward pass. Object classification is a task that predicts objects in the image, and object localization is a task to identify the location of objects in an image and render bounding boxes around them. SSD also uses a multi-box method for fast class agnostic bounding box coordinate proposals. The baseline model uses Inception v2 as the feature extractor. This enables to robustly recognize various objects by extracting visual features which can provide a semantic representation. During inference, we load an unlabeled test image. Then we load the trained baseline model, which would include both a model graph and weights files. The loaded model would also be used to make predictions. The predictions include XY axis coordinates of the bounding boxes and the object class number. This information is returned into the output file. The output file is processed to render bounding boxes on the output image. So these are some of the steps that is performed part of inference in this particular demo. And the next is a demo. Let me bring up the demo. So for the purpose of demo, we use Jupyter Notebook, and Jupyter Notebooks are very good for rapid prototyping. And the inference is set up by building Docker container, which uses GPU-enabled TensorFlow. Here we can look at some of the sample images from the data set. And as you can see, these images are at a higher end of 3000 pixels. And here we look at one of those sample images. This is a basic 3-channel RGB image with height 2700 and width of 3300 pixels. It's some of these cells are already run, so let me rerun some of it. So here, let's look at what are the unique classes that are present in this particular image. So here, what we're trying to do is we load the particular image, and there is also label information that is present for this particular image, and we're just printing those information here in the Jupyter Notebook. So there are around 9 classes, 9 unique classes, and there are passenger vehicles, small cars, bus, truck, trailer, and these are some of the objects that are present in this particular image. So this particular data, we already know what the objects are present. So for the inference step, we try to load an unseen test image, make prediction with the trained baseline model. So let's load a test image. So The first time I saw this particular image, I wasn't sure what these green patches are. I thought it was one of those weird golf courses in middle of nowhere. But let's see if the algorithm is able to predict what these objects are. So let me run the inference. So to run the inference, first what we try to do is we load the pre-trained baseline model here. Then we generate predictions. So here, as you can see, that it took nearly around 12 seconds. The inference is running on a T4 GPU. As you can see here, there are around 10 or 11 unique classes that are present in this particular image. And these numbers are the class numbers. These are not the count, but the class numbers that can identify the object, that we can use to identify the object. And let me write all this information back to the image. And we can see that the bounding box information is already written to the image. So let me open all the output is stored in this prediction output. And here you can see that this was created a minute ago. And, okay, so these are object number 44, 41, and 51. Let me see what is 44. So 44 here is a tugboat. So I was wrong. So it's not a weird golf course in the middle of nowhere. And you can also see that there are a lot of 73s, a lot of 18s. Let's see what 73 and 18s are. So 18 is a small car and 73 is a building. Let's see what other objects. There were, okay, since it's mostly in the city, you can see a lot of buildings and small cars. Another interesting thing about this XView data set is the satellite images are captured at different times of the day. So this would be useful to create a generalized model. Well, that's it from me here. For some of the other cool projects we work on, please check out HPC at Dell.com or delltechnologies.com/innovation lab.